Some people may ask, why do you need another qubit, right? You already have a few qubits that work well. And the honest answer is we should explore many different opportunities. Hi, my name is Andreas Heinrich, and I'm the director of the IBS Center for Quantum Nanoscience in Seoul, South Korea.
Why is everybody talking about quantum computers?
Quantum computers are an amazing concept. They may allow us in the future to do some computations that are very difficult to do on normal computers much more efficiently. So this may allow us to solve certain problems that we currently cannot solve. So let's maybe look at what makes a quantum computer different from a classical or normal computer, right? In a normal computer, we have our so-called bits. That's the 0 and the 1, where we store all our information. In the quantum computer, we have something similar called the quantum bit or the qubit, but the qubit is a bit more powerful than a classical bit. It can store more information, and that particularly becomes important if you couple many qubits together to make a more complex machine.
Are there already working quantum computers?
There are quantum computers today. You can actually buy a quantum computer if you have a lot of money. But the practical applications of those quantum computers are still quite limited. So as far as I know, at the moment, you can only use them to do research on quantum computing. You can understand how they work and what the limitations are, but you cannot use them yet to solve a problem that you cannot solve on a normal computer.
How long do you have to wait for a quantum computer?
How long do you have to wait? That's a tough question, right? You're asking a basic scientist, how long is it going to be until the basic research is going to be a practical product? The honest answer is we don't really know. But if I had to guess, I would say in the next 5 to 10 years, we will actually see some computations that we cannot do classically with a normal computer, but we can do on a quantum computer. The most promising class of those are simulations of quantum systems. Those are important to know how molecules look, complicated biomolecules or pharmaceutical molecules, to know their structure. And for that, it may actually be very helpful to use a quantum computer. So my guess is we first will use a quantum computer to study quantum mechanical systems, but those may actually have real-world applications, such as in the pharmaceutical industry.
What does it take to make a quantum computer?
A quantum computer is a tricky thing because in the end, of course, everything is made from quantum mechanics. Quantum mechanics is the theory that rules everything around us. But when we say we want to make a quantum computer, we mean something very specific, not just everything is quantum. What do we mean? We need several ingredients for this. One is you need to have the actual active ingredients called the quantum bits or the qubits. You need to couple those qubits together to have multiple qubits, and you need to control these qubits. The problem, though, is that if you want to control the qubits from the outside, they interact with the outside, and that destroys their quantum information. So it's a very delicate balance between, on the one hand, having them perfectly isolated so that they don't talk to anybody, but you do need to talk to them to do something useful. And it's this competition between having an isolated quantum system and a quantum system that you can actually interact with that makes quantum computing so difficult to implement in practice.
What kind of qubit platforms exist already?
There are several qubit platforms that the scientific community has developed over the last, it's not that long, maybe 20 to 30 years, right? There are two that come to mind as the most promising ones that most people talk about nowadays. On the one hand, that is superconducting devices, so actual materials that are superconducting at very, very low temperatures. And those superconducting devices can act as a qubit, and you can couple them together to make several qubits. On the other hand, you have the more traditional quantum system, which is basically an atom. You can take these atoms, you put a charge on it, then we call it an ion, and then you can hold such an ion in the middle of a vacuum chamber, literally in vacuum, in nothing, basically. And then you can use light, lasers, to control the quantum states, and because they have a charge, they can talk to each other, so you can have multiple qubits interacting with each other. That's a so-called ion-trap quantum computer. And so you have these two front runners, I would say, but they all have problems. And maybe we want to talk about problems and solutions.
What are the problems, and is there an alternative?
First, let's start with the superconducting devices, right? A superconductor is a material, for example, niobium or aluminum, right? It's actual metal, it's a real material you can touch. The problem with those is that they are very big. They're actually on the scale of millimeters. So if you want to make millions of qubits that are each 1 millimeter by 1 millimeter in area, it's in practice not really possible, right? So you need to make them smaller again, and then they become more prone to this decoherence, this unwanted interaction with the environment. On the other hand, we have the ion traps. Those are ions, as I mentioned before, that are held in a vacuum chamber. And of course, it's a little bit difficult to see how can you make a practical device with this. It's a beautiful research tool, I would say. Now, those are two platforms, and what we do is we add another new platform to this. And that is actually to take a material, make it perfectly clean and flat, and then we put our quantum bits, our qubits, as atoms or molecules on top of this clean substrate.
How can your platform compete?
A new platform for qubits is, of course, a very exciting thing because we only have a handful of platforms at the moment. So if you add another one to this, you may have something that is better in certain aspects, right? But of course, a new qubit platform also has to compete with the existing qubit platforms, right? So how do our atoms on a thin insulating film, our qubits, how do they compete, right? They compete very favorably in the sense that they are very clean. There are no defects in the environment because we control everything down to the atomic scale. We know where every atom is and what the atoms are. And so they enable us to do something where we can really say we put one qubit exactly 1 nanometer away from the next qubit, and not 1.1 nanometers, but exactly 1.0 nanometers. And this allows us to do some engineering on the atomic scale that is not possible in any other qubit platform. Now, I also have to be honest with you, on the downside, of course, we're currently dealing with 1, 2, and 3 qubits, and not with 1,000 qubits, right? And so we have some pros and some cons.
What role plays your latest paper?
Okay, so the idea of having an atom or molecule on a surface as a qubit is a relatively new thing. This has only been around for, I say our first paper on this was 4 years ago. And actually just this year we demonstrated the full quantum coherence control of a single qubit. Now this new paper that we're just publishing now actually takes us from a single qubit to multiple qubits, to 2 and 3 qubits. And the really exciting thing about this is that we actually found a way to make these so-called remote qubits. So the qubits that are not just in the center of our device, but a little bit outside, and that we can still coherently control them at the same time as the one that's in our center. Right? So we have a multiple qubit platform now that is a really new development for the spins on surfaces.
How does it feel to be in the middle or even leading a field in the race for the best qubit platform?
It is an amazing concept for me personally to think about. Now we are actually in the world of qubits and we are competing with other qubit platforms. This is not something that comes natural to me, quite honestly. And I want to say I'm at the core a basic scientist. I don't really am an engineer. I don't really want to build a quantum computer with 1 million qubits or something. But I do want to understand how the world works on this very atomic and quantum scale. And this helps us and helps also the engineers that want to build practical quantum computers to maybe learn more about how the world really works on this scale and how we can harness this power of quantum for practical devices.
What was the most exciting thing you have ever done with a single atom manipulation?
My expertise really lies in studying surfaces of materials with atomic scale precision and putting atoms and molecules on those surfaces and then build structures with atomic scale control. Right? This is a really cool and unique aspect that we can do with our research tools called the scanning tunneling microscope. Now, in the framework of quantum computing, what I find the most amazing is that the inventors of this tool, the scanning tunneling microscope, some 40 years ago, did not possibly imagine that we could do quantum coherent manipulation of one and now multiple qubits on the surface. And I just find it truly amazing that over the now 2 or 3 generations of researchers, we have taken a really cool research tool that was built to basically see atoms, to also then to move the atoms and build structures, then to do spectroscopy, and now we can do quantum coherent manipulation with those things. And it's amazing to me that there's no end in sight. We can always do new cool things And so every time I make one of these developments, I get super excited about this, and I forget how excited I was about the previous step, right? So I would say, of course, the most exciting is what we do right now.
What was the biggest challenge during the research on this qubit platform?
A qubit is a delicate device. A qubit has to have a way that we can control it from the outside, right? We have to be able to interact with it and change its state and to measure its state. But at the same time, it needs to be isolated from the environment. So if it couples too strongly with the outside world, then its quantum behavior will be destroyed. And as in all qubits, it is this delicate balance between being able to interact with the qubit and being able to shield the qubit from the environment that makes this delicate balance. And that was the most difficult thing for us here also, to achieve a way to control the qubit without destroying its properties.
Is this success one of the reasons why you became a physicist?
I'm a physicist because I like exploration. I like to understand how the world works. And I like to see how, actually in my case, how do atoms and molecules talk to each other, and how can we harness this to do something potentially useful, right? But in the end, I'm really most interested in to understand what happens when you have this kind of level of control on the atomic scale, and see what we can actually do with that.
What is the biggest advantage to work with a big international group of researchers?
One of the fun facts about this paper is that it is a very international collaboration. There's a research group from Japan, there's a research group from Europe, a research group from the US, and of course our main contribution here from the IBS Center in Korea. Right? There are students on the paper, there are postdocs on the paper, there are senior researchers on this paper, right? And it is truly stunning to see how people can come together and solve a complicated problem, such as how do you make remote qubits and how do you interact with those qubits, and come up with a solution together, and then work together to find a way to make this possible.
What is next?
What is next? Always the most difficult question last, right? What is next? For us, there's kind of two ways to answer this question. What is next? One is we keep exploring. So most of the research we do here in the Center for Quantum Nanoscience is actually exploration, maybe find new qubits, use qubits for quantum sensing, and many other things that are more in the basic science realm. But here we are in the realm where we actually are competing with other qubit platforms, and there are two obvious things we need to do. One, we need to increase the number of qubits. We need to see what are the limits here. Can we go to 10 qubits? And I believe we can go to tens to hundreds of qubits with this particular platform. And the second one is we need to make our qubit even more reliable. We need to make it have a longer coherence time so that we can do more quantum operations. And those together, they may show that this is a particularly strong type of qubit in comparison to other qubits.